Hey everyone, we're going to look at numbers 4 and 5 in section 2.7 real quick. And in both of these limits, they are limits at infinity. We say we're going to use this important relationship that I developed in the lecture videos for this section. For any constant r greater than 0 and any constant c, the limit as x goes to infinity or negative infinity, whichever one, doesn't matter, of some constant c divided by x to the r power will always be 0. And the reason being, if r is greater than 0, then x to the r, that value is getting larger and larger in absolute value as x goes to infinity or negative infinity. Whereas c is some constant, no matter how big it is, it stays the same. And so this denominator just gets bigger and bigger in proportion to the numerator. Overall, the fraction, therefore, is getting closer and closer to 0. We say the limit is 0. This is very important that you understand that relationship. Okay, so when we're doing 4 and 5, they're very similar. They're just the limits of rational functions where we have one polynomial. This is the actual limit here. One polynomial divided by another. Of course, as x goes to infinity, 12x goes to infinity, and 13x minus 2 goes to infinity. So we say this form of this limit is infinity over infinity. This is an indeterminate form. Again, that doesn't mean the limit doesn't exist. It means we've got some work to do to find this limit. So there's a couple of ways you can do these limits. Some of you are very familiar with these because the same sort of analysis applies when you're talking about finding the horizontal asymptote for rational functions, which hopefully you did in pre-calculus. But here, the one technique to get this limit to come in is to divide the numerator and denominator by the highest degree term, the highest degree power of x, let's just say highest power of x, right, in the denominator. It's important that you do that in the denominator. So the highest power on x is 1. So x to the first power, I want to divide both the denominator and the numerator by x. Notice I have to do the same to both the numerator and denominator to make an equivalent fraction. So if I divide 12x by x, I just get 12. 13x divided by x is 13. And 2 divided by x is, well, 2 divided by x. And then what we do is we're still taking the limit, of course, as x goes to infinity, right? And then what about 2 over x? Well, as x goes to infinity, by this limit we talked about, that's going to 0. The 12 and 13 remain the same, and so the limit becomes 12 divided by 13. So 12/13 is our limit. Okay, so this is one way you can show that limit. Another way is to just think about, for large values of x, in the denominator here, the 13x and the 2, the 13x is going to dominate. I mean, when x is a billion, you'll have 13 billion and then minus 2. Well, that 2 is insignificant in comparison to 13 billion. So in other words, what we can look at is just the limit of the highest degree term in the numerator over the highest degree term in the denominator. And so that would look like this. So the limit of this original rational function is the same as the limit of this rational function. These functions are not exactly the same, but for large values of x, they are very similar. And in fact, the limit as x goes to infinity for both of these is the same. So what can we do now? Well, 12x divided by 13x, I can simplify, right? Divide top and bottom by x, and I just get 12/13. Well, what's the limit as x goes to infinity of a constant? It's just that constant. And we get the same thing. For number 5, very similar then. We have a polynomial up top, polynomial in the bottom. Again, as x goes to infinity, we get this indeterminate form. Here, the highest degree term in the denominator is x to the 4th. So I can divide top and bottom by x to the 4th. And when I do so, 2x squared divided by x to the 4th simplifies down to 2 divided by x squared. 5x divided by x to the 4th simplifies to 5 divided by x cubed. 7x to the 4th divided by x to the 4th is 7. 5x cubed divided by x to the 4th is 5 divided by x. And of course, 12 divided by x to the 4th. But then we realize that each of these fractions here, the numerator is a constant, the denominator is some positive power of x. So they're all going to 0, right? Every single one of these is going to go to 0 as x goes to infinity. So what are we approaching? 0 minus 0, which is 0. 7 minus 0 minus 0, which is 7. And then 0 divided by 7 is just 0. There it is. Limit 0. Or, as we talked about before, you could take the highest degree term up top, which is 2x squared, and divide it by the highest degree in the bottom, which is 7x to the fourth. Simplify that, right? Taking the limit of this function is the same as the limit of this one as we described above. Well, you can divide top and bottom by x squared, and you get this. And then as x goes to infinity, this is that same form of a limit that we have above, right? Technically, remember, you can rewrite this as 2/7 divided by x squared. So it's still a constant divided by x to some power. That's going to go to 0. Okay. All right. So these are really easy. You can find these limits, I hope, almost by inspection, because you kind of can tell what happens when the degree of the top is less than the bottom. Like we have in this case, the limit's going to be 0. If the degree of the top and bottom are the same, the limit is going to be the ratio of the leading term coefficients. And in another case, if the degree of the top is bigger than the bottom, then that limit is going to be either positive or negative infinity. Okay, I hope this is helpful here.